Okay, let's start the first part of 4.4, which is energy in reactions. Still in topic 4, but the last subtopic. So in this subtopic, you will learn, or you will be able to do, identify a reaction as exothermic or endothermic given relevant information. Secondly, explain the endothermic or exothermic nature of dissolving ionic substances in terms of the law of conservation of energy, the energy required for dissociation of ions, and the energy released by hydration of the ions. You also will learn how to write thermochemical equations and the dissolving of ionic substances in water. You will also learn some other calculation techniques, explaining the following relationship and undertake calculations involving those formulae there, and also rearranging them. Experimentally determine enthalpies of solution, which you would all do SACE prep on it. And finally, you need to be able to identify a reaction as exothermic or endothermic given a thermochemical equation or the value of its enthalpy change. All right. We'll firstly look at gain or loss of energy in chemical reactions. Now, photosynthesis that plants do, it is, well, clearly an absorption of energy. It absorbs sunlight to cause some sort of reaction. So it is considered to be an endothermic reaction. The quite opposite of that is combustion reaction. It is a release of energy and exothermic reaction. So by reactants reacting with each other, it releases energy to the system, or outside. Now, you will hear a few different words and also letters that you might not be familiar with. First of which is enthalpy. Letter is H. It shows how much energy is stored chemically, or heat content of the system. So the system could be a place or a container where all the reactants and products are stored, and reaction could be happening. Units for enthalpy is joules or kilojoules. And you could have molar enthalpy change of reaction. You could simply say enthalpy change of reaction though. It is a change in heat energy content measured at constant pressure. So enthalpy, just one above, is a energy stored, right? Enthalpy change of reaction tells you how much energy can come out or can go into chemicals. Often it is expressed in per mole of reactant. That's why the word molar is in brackets there. So it could be joules or kilojoules, but also joules per mole or kilojoules per mole. Because you're dealing with number of moles in those units, you can easily convert it into joules per gram or kilojoules per gram as well. A lot of heat density is calculated with these units or expressed with these units. The term enthalpy, it is also called the heat content of substance, the sum of kinetic energy and potential energy of the atom, ions, or molecules of a specified amount of reactants and products. Oops. It is also represented by the following expression. So, if you have got delta H, so enthalpy change of a reaction, that should equal to H, so that is enthalpy of products take. enthalpy of reactants. So where you ended up, where you began can be taken out from where you ended up. Then you should be able to find enthalpy change. Hope that makes sense. All right. Now you can also translate that equation just then into what's called energy profile diagram. So it usually has x and y axis with 0 on it. X axis is reaction progress, and y axis show energy in kilojoules per mole. If you start with reactants which have quite a lot of energy stored, the line will be fairly high. And if you end up with something a lot more stable and less energy stored, the product's line would be somewhere lower than the energy. Now, reaction progress would look like that, because even if it's like burning petrol, you would have to give a bit of spark for the reaction to start. So some energy is required, but after reactions finished or during reactions happening, what's also happening is release of energy. So delta H equals to, well, delta H product, which is lower, take delta H reactant, which is higher in the energy profile diagram. Delta H is considered to be, well, will definitely be a negative number. Delta H is less than 0. What that means is that energy is released to the system, meaning this energy profile diagram shows exothermic reaction. Okay, so for exothermic reaction, reactants always have higher energy stored, enthalpy stored, and products have less of enthalpy. So those who have guessed, we have got another energy profile diagram. The word profile is missing. Same deal, you've got x and y axis, reaction progress, and energy goes up on the axis respectively. Only difference here is reactants that you start with is much lower, in the lower range of energy profile, and products would end up somewhere high up there, meaning reactants that you started off with gained energy from somewhere. The energy profile diagram in between there would look like that. Well, that should be shifted to the left a bit. Should be a connected line. My apologies. But energy-wise, where you started off was where the reactants were and ended up at products. So that's the difference. Now, the direction of arrow also shows that the change of enthalpy was positive. If you take reactants from products, you will have positive difference. Delta H is larger, greater than 0. Meaning energy was absorbed from the surrounding, which means it's an energy profile diagram of endothermic reaction. So as a summary, if delta H, so enthalpy change of the reaction, was larger than 0, it shows that it's an endothermic reaction. For example, if you dissolve ammonium chloride, which is solid, into water plus AQ, that would cause NH4 and Cl to be aqueous, so ionic substances, ions. Delta H, if you notice that has got plus sign on it, meaning ammonium chloride is dissolved in water, it absorbs heat from the surrounding. And if delta H, so change in enthalpy, was less than 0, we know that it's an exothermic reaction. Example would be NO gas and ozone gas, O3, reacting, producing NO2 gas plus O2 gas. So delta H equals to negative number here, negative 183.0 kilojoules. So when nitrous gas, oxide gas reacts with ozone, it releases heat. So that's the summary for this part. And you can find a question regarding this on page 126.